Hi, and welcome to Gravitational Fields Lesson 4a. Today we're going to be really delving into potential energy and looking at what that means. We start with two statements. A ball has 100 joules of gravitational potential energy. This is something that we've been dealing with since GCSE, which shouldn't be a problem. We've got an idea that balls, if we hold them up in the air, can just have gravitational potential energy. The V, or potential, of the field is 100 joules per kilogram. So what's the difference between these two statements? This one is talking about a given mass having a certain amount of potential energy. The second is telling you about the potential of the field at a specific point, because it's very rare that gravitational fields are constant. They normally change as you get further away from the mass. Gravity of Earth is very strong on Earth, but as we move further and further away from Earth, the gravitational field strength will drop and drop, which means also we'd expect the potential of the field at a given point to drop. So what does this mean? It means if you've got a kilogram of mass at that point in the field, it will have 100 joules of gravitational potential energy. If you've got a 2 kilogram mass, it will have 200 joules. If you move further away, it will have a different amount of potential energy. If you move closer, it will have a different amount of potential energy. So we define the potential of the field at a given point. And what I've got here are some of those equipotentials that we were looking at last week. So if you had a kilogram of mass here, it would have minus, because remember, gravitational potential energy is always negative, 150 joules of gravitational potential energy. That's what this minus 150 means. It means anywhere along this equipotential, 1 kilogram of mass will have minus 150 joules of gravitational potential energy. At this point in the field, it'll have minus 100. At this point, it'll have minus 50. As we go closer and closer to infinity, remember infinity being infinitely far away, we'll trend towards 0, because we define the potential as 0 at infinity. I've now drawn two different fields here. There's a difference between them. Pause the video, take a moment, see what you think is the difference between these two fields. Well, in this field, the equipotentials are closer together than in this field. Meaning that if you move a certain distance in this field, your GPE might change by 50, but if you were to move the same distance in this field, it might change by 200. So this means that this field is stronger than this field, which makes sense. You'd have to put more joules of work in to move it the same distance in this field than you would in this field, which means you'd expect this to maybe on Jupiter. You're having to really put energy in just to move it a little bit, as this might be the moon. Small amount of energy, big movement. So we'd expect this to be a stronger field. Now we can actually look at the maths of this in quite a neat way. We can define gravitational field strength around potential. We can say that the more the potential changes for a given distance, the stronger the field strength is. Because look, here we've got a smaller change over a given distance. This one we've got a bigger change in this distance. So we can say the gravitational field strength is equal to the change in potential divided by the change in distance. And whenever we're talking about fields, we define distances in radii, how far away you are from the thing. However, gravitational field strengths are always positive because they're forces, potentials are always negative, so we have to put in a cheeky minus just to make the maths work. So we can say that field strength is equal to change in potential divided by change in distance. So this one is going to be a stronger field than this one, which would make sense. Now I'm going to be formalising this a little bit more in the next lesson, but just have a go at the question underneath, and I'll see you in the next video.